So let us see what we have so far. Right. So let me just say we want to understand the conjugate of a permutation. Right. So basically sigma was this permutation that we started with, and we would like to understand this. Right. Yeah. Let's just call this sigma prime. Then can you tell me what we know? I mean, you may have figured out everything, but where we ended? What did we do? We said that sigma 1 inverse of AI is equal to sigma 1 inverse of AI plus 1. Is it correct?
Yeah.
That's correct. Okay. Right. So now we want to see what happens to this. Given that J is not equal to sigma 1 inverse of AI for any I. We want to say that J is fixed. So how do we show that? So let us apply. So then this is J, right? And what is this? We're just using associativity. So this is sigma 1j, right? And what is this condition? This condition is just saying, actually more simply, it is just saying that this is not equal to any AI, right? It's better way to say. What does that mean? That means that sigma will fix it, right? Sigma will fix this sigma 1j. And then, yeah, basically, you know why I said it, because I want to prove something, but logically it is explained also. Yeah, sigma 1j. Okay, correct. And then this is equal to j. So we proved it. Okay, but I mean, there is a better way to prove it. But what we have done, then that way is actually better. Okay. But then you see there is a thing that is happening here, right? That if you do not partition your numbers from 1 up to n into these two classes, right? Those which are of the form sigma 1 inverse of some AI, and those which are not of the form, right? Then the proof becomes slightly, then it becomes slightly more difficult to arrive at this answer. Okay, it is still possible. Everything is just calculation, but yeah. Okay, so we have proved this is somewhat like what Arnav was saying, but obviously it's because my definition was slightly different. That's why. So if I change the definition to this, then we get precisely what Arnav was saying. And that is basically what you get throughout mathematics. Right? It's just a change in coordinates. So then we forget this notation that was just an intermediate. Okay. Right? That was just an intermediate. So this is, so all these calculations have to be done and observed and so on. Maybe I did this calculation 4 years back, and so I am little, yeah. And actually nowadays I don't we don't do much of this cycle type. I'm not doing much combinatories these days also. So yeah, at one point we did a lot of things in this, but now it's slightly slow calculating. So we get this. But you see, I mean, there are actually you can avoid all calculations, I think, to be honest. But okay. Yeah, am I audible?
Yes.
Okay, someone called. So yeah, so let me give you some hints, and so maybe, yeah. So prove that, maybe I'm stretching this topic too much, right? Maybe like I'm not doing anything. I'm just writing same thing again and again. Feels like, so sigma. So yeah, this prove that this is equal to j if just what we proved, j is not equal to sigma 1 inverse ai. Okay, in a different way. Okay, by showing that this is an n cycle, k cycle. Okay, and that you should do by considering Sn to Sn an automorphism, which is given by sigma going to, this sigma is an arbitrary sigma. Maybe I should use a different notation, but you get my point. I'll not use, because you should get used to the context here. Context is, this is a different context. Arbitrary sigma gets up to this. Okay, sigma is, yeah. So if you consider this automorphism, then you should be able to show directly that cycle types are preserved, right? You should be able to show that cycle types are preserved. Okay, or at least to begin with, you can show that if something is a cycle, then it goes to a cycle, and that you show, that is not difficult. Yeah, and yeah, I actually don't know if it is more difficult than, less difficult than this, because characterizing, yeah. So my claim, what I'm saying is that to prove that a cycle goes to a cycle under an automorphism, but for that you need a characterization of a cycle which is group theoretic. Abhi रहने दो. For that you need to characterize a cycle using group theoretically, right? Means that in terms of, without alluding to any elements. Yeah, cycle length is fine because that's the order of the cycle, right? So if you can prove that it goes to a cycle, then cycle length will be same, because that's order. That's a group theoretic property, which order will be preserved under automorphism. But actually, all these things are possible. It's only that I don't know how to characterize as some permutation is a cycle. Yeah, right. Saying that something is a cycle using some properties of groups which are preserved under under isomorphism. Yeah, I think I don't know that. So in that case, without doing an explicit calculation, it would be difficult to describe, I think. Okay. Yeah. So maybe no. Sorry. Yeah. But still, I mean, something to learn, something to understand. Yeah. Yeah, I see. So that was all right. So this is what we get. And here you see we did not assume the explicit nature of sigma 1. You observe that. That was not useful. So what happens after this? What happens after this? So you can see that it's a K cycle. It can be done some complicated way, some induction and stuff. But yeah. So but if you're doing this, so now how to describe this set? Any answers? Now you can just answer this. Sigma 1 is changing, so you have the freedom to change sigma 1.
It will be the conjugate will be all K cycles.
Exactly. Yeah. The conjugacy class, right? The conjugacy class will be all K cycles. Yes. Yeah. So that's why and then you can see that because, and I'm not proving this, you can do it. You just see. You have to just change sigma 1. You want any K cycle, just take a permutation which sends A1 to AK to those numbers. Okay. So from here, and then you generalize it to general permutations. It's just easy. You just patch up the things, and then you prove that if I do not assume anything about meaning, if I now just write, so we are almost done. Yeah. But you should write the proofs. It's important. If sigma is in Sn, okay, yeah, sigma is in Sn, then this is all permutations of same cycle type, right? You get all permutations of same cycle type. Correct? So just take a minute and see if this makes sense. Cycle type I am not defining. Cycle type is basically a permutation, right? So see if I need to define cycle type. Let's check. No, right? So it's okay. So then the question is how many conjugacy classes will be there? Meaning, is this some other known combinatorial quantity? So think about what is a cycle type. If you think about it very clearly, then there is no problem, right?
Okay, so if
Hmm.
it says some, so one is identity, and there will be other n minus one type of cycles.
Okay. Yeah, identity will be in its own class. And tell me, what is the cycle type of identity? Then it will be understood if you have understood the definition of cycle type. So what is cycle type? See, knowing what is cycle type in your mind is different from defining it. So try to define what is cycle type, and maybe, yeah, I'll say what is cycle type of identity, means identity permutation. Yeah. And then tell me the other things. Yeah, right. Because what should be the cycle type definition, and then what should it be for identity? Okay. So let me give you some permutation, and you tell me the cycle type of that. That's the next thing. If you cannot define something, then you take an example. So firstly, the permutation has to be, as Vaishnavi was mentioning once, uh, permutation has to be in, means I'm writing it in disjoint form. Yes, I think. Anything? Vaishnavi, you want to say anything?
Yeah, like length of this would be the cycle type. Like length of each one for it's 1, 2, 3. The cycle type.
Yes. So it is it's sequence, right?
Yeah,
It's a sequence
yeah.
in some sense, and
Okay.
you have to say it in slightly more is there
We
in
can also
non-decreasing.
say uh, n cycles of length one or something.
That's another way. Yeah, that will also work. That's a different. Yeah, that's another way.
Actually,
Right.
I'm not getting what are you talking about cycle types. So after she said,
Yes, correct. Yeah, so you have to make the closest obvious interpretation. But yeah, and that I agree that it's vague. Yeah, so get the definition out of you. That's what's the attempt. And you're right. I mean, you're getting to give a definition. So basically, this is 3, 2, 1. Okay, but you see, it's in the non increasing order I've written, and that is important. You can understand why. I will not explain. Okay, because you get the same permutation if you permute the cycles. So we arrange it in some order. You fix a stand note either you want to arrange it decreasing or whatever, and then yeah. So basically it's just this, yeah. Or as Arnav was saying, number of cycles of length one, number of cycles, many things you can say. Yeah. But basically every cycle type is a partition. Correct? Yes or no?
yes,
Yeah.
yeah,
Every
yeah.
cycle type, yeah. These are basically partitions of n. And so this so you define it, and then this will be number of partitions. Number of partitions of n. And you know the definition of partition. This is the beginning of what is called representation theory of permutation groups. Okay, there are books written on this. There is research going on in this. Okay, I was reminded of something, so I was reading a little bit. And this is not research; this is old stuff which I was reading. The current research, I can probably not read most of it, but representation theory of SN is a very wide, is a very so many young generation mathematicians, especially so especially the IMSC is sort of the place in India where people do this, the hotspot of this representation theory of SN. Okay, yeah, more than CMI, they do all this. They do this more than CMI does slightly different stuff, but representation theory of SN is, you can say, combinatorial representation theory. Yeah. Basically, you have this SN, which is a group, and again you look at something called group ring. So you make a ring out of it, and then you look at modules over it, and then you try to say what are all the modules. There's a way to describe all the modules, which is basically saying that you describe all the group actions of SN on finite dimensional vector spaces. Describe all the group actions, and all meaning you have to have some notions between isomorphism between two group actions, and you can feel, if it's mathematics, then there should be a way to give an isomorphism between two group actions when two actions are same in some respect, sort of mathematically, if there's no difference. Then so basically all group actions of SN on finite dimensional vector spaces, you yeah, that is slightly incorrect, but you can assume that. Yeah, slightly incorrect, but you can assume. And classifying all the group actions. Okay. So for that, you need to first have a notion of what is similarity between two group actions. What does it mean for two group actions to be isomorphic? And second, you need to have a way to decompose group actions, which is sort of like orbits. If you have a group acting on a set and it's forming orbits, then you can basically understand the action or each of the orbits, right? There is no difference. You don't have to consider the different orbits together, correct or not, right? From a group action perspective, you may still have to consider them together if they form some equation and something. But so those are what are called now irreducible, which is only one orbit, and action is called a representation because you take certain kinds of action, and finite dimensional. And when you combine this, you get something which is a center of algebra, combinatorics, and geometry. So a very nice place to read all this, then try to read this at some point, is Fulton. Actually, I attempted to read this book. I read a bit. Yeah, you may not be able to read that much, but some parts you can read very easily because it's just baby things he does. But through Rose, actually, you can discover a lot of things. That's interesting. Fulton, I think, I not. I think I know is William Fulton. The yeah, again, I think it's correct. And Fulton, I don't know his research area. I don't know his research area in particular because he has books in several. But coming to the point, he has this book which is called Combinatorics. I in fact have the book with me. Combinatorial, no, Combinatorics of Young Tableau. Okay, I forgot the name of the book, but if you just take, yeah, that's what happens. Yeah, Young Tableau. Okay, so yeah, this is a very famous book, and his book on, and Young Tableau is something which is you can approach it from any level of maturity. You can start doing it. All kinds of people find employment in this. Okay, people who just do combinatorics, they find employment. People who do algorithms, they find. Donald Knuth, Donald Knuth, a great computer scientist, he has some algorithms in this. He did not know representation theory. At least formally speaking. Yeah, but he contributed things in this. Yeah. So if any one of you interested, you can read, and you can, if you want, you can present some chapters from this book. I will love to listen. Just as a listening, yeah, and yeah, just learn, yeah. So, anyways, so and then it turns out that in fact all representations of, yeah, that's the main thing I did not say, that here you have conjugacy classes, but this is just a tip of the iceberg. All group actions of this are actually also in correspondence with number of partitions. Like here, you are saying that the permutations are in cycle types are in correspondence with number of partition, one-to-one correspondence. But in fact, there is much more. Okay, and why is that true? That's not very difficult, but probably that needs some theory, some theorems. It's difficult to say now. Okay, so we will stop here, and yeah, then the next thing which comes is conjugacy classes of AN. That is we should do. Okay. But I don't think we will do it today. Today is not a Sunday, so I cannot go forever. But let me just mention the result. I mean, I want to do it. That's why I'm going on and on. So about AN, maybe I will do it next day. But maybe, in fact, I'll just share screen and show you. Because I've just been looking at this here and there, so I'll share it. So it's there in Dummett and Foote. And AN is a simple group. That is the interesting thing. That in fact, there are no normal subgroups. Okay, you get my point, right? There are no normal subgroups. AN is a simple group. There are no normal subgroups, and you see that actually tells you that it has no. Maybe I'll just say, otherwise probably confuse you if you look at the book together. So let me just tell you that here. So I'll just give me 5 minutes, and then we'll go to have dinner also. If dinner gets late, then it becomes a problem. In the morning, then I'm very slow if dinner is late, and I'm slow to get going in the morning. Okay, so what I'm just saying is, first thing is, and this is, you can take it as a home. So Dummett and Foote, you should read this. Dummett and Foote. It's last section of group actions. Last section on group actions. This gets into some very, very interesting mathematics. So if you look at the last section on group actions, then they prove that AN is simple. Okay? Simple means it has no normal subgroup. Okay, no normal subgroup. Okay? Yeah. In the beginning, what I said was slightly wrong. I take that back. Yeah, slightly wrong. AN is simple means it has no normal subgroups. Means that what does it mean? It means that, of course, you know what it means, but if I have to say it in the perspective of conjugacy classes, it means that so it certainly implies this, that if you take any subgroup, okay, just hear me and then you see if it's correct. Take any subgroup H of AN, okay, and then if you consider its normal closure, it just means take all possible this, right? This will be a group.
Yes.
Will it be a group? I don't
If
know.
we can find G such that.
No. Sorry. Yeah, I know if this is not a group, I know what to do. But no, this will not be a group. I'm sorry, because you see, why do you think this will be a group, right? You see, each of these things are groups, correct? That I think what Vaishnavi meant, right? I mean that is certainly true, right? H is a group. G inverse HG is a group. This you can prove because it's an image of a subgroup, image of a subgroup under an automorphism, under homomorphism. So the image of a group is a group. So it's a group. But right now, what you are looking at is sort of a union of groups. A union of groups is not a group, right? Otherwise, why do you have the concept of group generated if it was a group, right? So you take the group generated, right? And that actually you will never find a subgroup. You will get all of AN. Because this group will be normal by definition. That is clear, right? Is it? No. Yeah, yeah. If you take the group generated, will it be normal? Yeah, that is a problem, right? Yeah. Then what is a description of? Yeah. So anyways, I think yeah, because I'm a little hurried, so I don't think about it right now. But then I will just say it in some simple terms, okay? So AN is simple, that is a fact, which means it has no non-trivial normal subgroups. Okay. What I wanted to say is where I was wrong. That is important to notice. Okay, because otherwise it's a wrong idea, which I'm telling you. Is it doesn't imply. So this one does not imply that there are no non-trivial conjugacy classes. Okay. This doesn't imply that there are no non-trivial conjugacy classes, which means that it may still happen that you start with something in AN, I mean the even permutation, you can talk about that next time, but permutation, it may still happen that if you take the conjugacy class of this is still sitting inside AN. Okay. This does not, because this does not give you a normal subgroup. It's not a group. Conjugacy class of an element, like why should it be a group? Is there any reason to? No. And you can find counterexamples. So it's not a group. So you do get these proper subsets, okay? But it's not a group, all right? That is, yeah, now I've figured out a way to say that thing, but leave it. Okay? This thing is still going to happen, but you will not get a normal subgroup. This fact is a bit non-trivial. And that's why I'm saying that you should, better if you read it here. I mean, I can discuss it next time. Maybe my presentation might be slightly different because there are hundreds of ways to prove these things, and you can see it. It involves, you can prove it with group actions, silo subgroups. You can prove it in many ways. Okay? Yeah. Some induction, A5. Yeah. So you should read. At least there will be part where they will do A5 is simple, and he's going to use group actions so that you can do. Okay. In fact, this A5, as I have noticed here, is I was reading online. I think they're saying that this is PSL isomorphic to PSL. Okay, forgot this. Yeah, which one it should be? I'm not sure. But it is isomorphic to one of those projective thing. Okay, I mean it has to be some finite field. So I don't know, probably Z2 or something. Z2, most likely it's Z2. Yeah, it's 2 integer module 2. So those are the kind of something. Some cardinality argument you can arrange it, but okay. So it's simple. Okay. So this is sort of your first example of a non-trivial example of a group which is simple. I mean, obviously, you have the groups of prime order, right? Groups of prime order, they are simple, but that is because they don't have any subgroup, right? But this A5, forget AN. Probably you cannot do anything right now with AN, but A5, we can do a lot of things. It has subgroups, but it has no normals. And proof of this you should read, and this is based on group actions. I think they have based the proof. They have written it in that section. That's it. Okay. Yeah. And this is your first example of a non-trivial, non-trivial example of a simple group, finite simple group. Those PSL things were not finite. Over at least over C, it was not finite. But these are finite simple groups. And you may have heard that there is a big project, which is probably the biggest, not exaggerating, it is the biggest project in mathematics. So classifying all finite simple groups. And you can read on Wikipedia, there's long history, and it's still, in some sense, it is still going on, and in some sense, it's finished. Okay. So, and AN is one of them. And fortunately, the proof of AN can be explained to anyone because we are anyone, right? We don't, what group theory do we know? Nothing. Almost there's nothing. Just definitions and some very basic. So this, we can understand it. That's the beauty. But others forget. I mean, they are very, very difficult. You need to know representation theory and then modular representation theory. In all ways, you can represent groups back to their origin, sort of back to their concrete realization. That's it. Yes, I'll stop here. And then yeah, I don't know. I think this class we will repeat on Sunday, and we'll continue on Sunday. And I think Thursday, I mean, this is Vaishnavi and me will be discussing some things. And yeah, I don't know. Time is 8:30, I think. Correct me. And we are doing basically what are we doing? Real analysis. Yeah. So we'll be looking at Cauchy sequences, Cauchy criteria, monotone sequences, and so on. Thursday 8:30 p.m. Okay. Yeah. All right, then we'll just meet on that time. Yeah. Good night.
This one, like they will be doing real analysis.
You'll see, yeah, real analysis, but yeah, on paper, yes, real analysis. Yeah. Okay.
Okay, Shomna, one more thing.
Yeah.
I need one day lonely actually to. I have to discuss some topics out my dissertation of third year.
Okay.
So, sir has suggested some topics, so I don't know how to find them and where
Okay.
to.
Yeah. Then we can discuss it maybe on Friday or something. Yeah. Is that
Okay.
right?
Got it.
Is that what you're trying to say? Yeah.
Yeah, okay, that's fine.
Okay. Yeah. So Friday maybe 30 minutes. So maybe Friday 9 p.m. is fine, but Friday 9 p.m. But just send me a mail. Okay.
I will be joining you Thursday or Friday.
Thursday though is an optional class. Okay. Thursday 8:30. There we will do these things, real analysis thing, as I talked to you. Okay. And Friday for your project discussion, we can do that on Friday. Is it fine, or do you want to do it earlier?
I uh, I just need 30 minutes only. I just to
Huh.
talk.
So let's do it on Friday. Let's not do both the things on the same day. Okay.
Okay.
All right. Okay. So it's confirmed. Let's meet on Thursday 8:30, and yeah, will be interesting topics.
Okay. One more thing. Maybe Friday I will be returning home. I'll be on train. So better it would be if we can do it tomorrow.
Okay. Okay. Yeah. So tomorrow. Yeah. Then okay. Then maybe tomorrow 10 p.m. Okay.
Okay, no problem.
15-20 minutes we can just discuss it quickly.
Yeah.
Okay. All right.
Okay.
Thank you. Thank you. Then tomorrow 10
Tomorrow
p.m.
10. Okay.
10 p.m. Okay. Bye.
Good.
Take care. Yeah.